Good morning, Physics 30. I hope you guys are having a good day so far. Welcome to looking at atomic spectra and the quantized model of the atom. So this is a really, really cool topic. And for me, what is the sad part is we would 100% be doing a lab on this if we were in class and getting to play with spectrometers and some lovely cathode ray tubes. It would be an absolute hoot. We'd have a great time, but we're in COVID lockdown. So that part makes me sad, but it's a cool lesson today. Hope you guys enjoy it. It'll be fun. All right. So ladies and gentlemen, we alluded to in our previous video that Bohr studied, or that Bohr came up with the next idea of the electron that helped explain, well, why the electrons aren't just constantly emitting light and the atom collapsing, right? So this is kind of the introduction to that next topic of what Bohr explained and some of the experiments Bohr did to come up with an explanation for this. I've also got a couple of YouTube videos for you on Google Classroom, which I'll be referring to in this video as well to help explain this concept too. All right. So ladies and gentlemen, Bohr studied the hydrogen atom because hydrogen is the simplest of all the atoms, a proton and an electron. That's it. You can't get, as far as an atom goes, you can't get simpler than that. So it was a really good one to study. And he developed a theory that helped to overcome the Rutherford's model's shortcomings that couldn't quite explain some of the nuances of the atom. Okay, so from a bunch of previous scientists, what Bohr knew, and once again, remember, as I mentioned, that was Physics 20 I mentioned yesterday. Isaac Newton said, if I've seen but a little further, it's by standing on the shoulders of giants, and how your success is built on the successes of other people. So it was the same with Bohr. So he knew that if you shone white light through a prism or a diffraction grating, the white light would be dispersed or separated into its individual wavelengths. You guys remember that? Yeah, diffraction. Okay. So this rainbow pattern that you get, so you see here, is what is called a continuous spectrum. So one wavelength right after another, all line up in one beautiful continuation of color. Sounds good? Okay. So Bohr, he knew that, and what he did is he took a gas, all right? So, and it was unexcited. Now, what unexcited means is that it's cooled. It doesn't have a lot of energy to it. And what he did is he then shone white light. So remember, white light contains all the colors of the spectrum, or all the Roy G. Biv colors. And he shone it through this cold gas. And then he shone that light that came through the gas through a prism or a grating. So what that would do is it would then separate the colors again. So what he observed was a continuous spectrum, but it had dark lines appearing in the spectrum. Now, what that tells us is that these dark bands show that these particular photons that had specific wavelengths were missing. Okay, now this is equation we're going to be coming back to because remember how frequencies, wavelengths, and energy is all related? So with this equation here, so this energy or wavelength or frequency, whatever you want to label it as, was missing from that spectra. So really cool. Really cool. And so what he called it was a dark line or an absorption spectrum. Okay, so a dark line or absorption spectrum. So here is your light source emitting a continuous spectrum. Nice cool gas. And as the light goes through the cool gas, then through, once again, either of these, doesn't have to be both, so either a slit or a prism. Okay, you're going to get this continuous spectrum, but look, dark bands are emitted. Now think back to color, ladies and gentlemen. What does the color black represent as far as wavelength and light is concerned? What does it do with light? It absorbs all of the light. That is why when you go outside on a hot day and you wear a dark colored t-shirt, you warm up a lot quicker than if you wear a white colored t-shirt. So the dark color is going to absorb the wavelengths. Well, guess what? We've got dark bands in the spectrum, ladies and gentlemen. These dark bands are evidence that this gas has absorbed those wavelengths. Isn't that neat? I know, it's cool. Super cool. If any of you guys have taken Science 30, you would know that we definitely talk about this, the spectra as well in Science 30. Science 30 is fun. Correction, if it has the word science in it, it's fun. All right, so ladies and gentlemen, Bohr concluded that this unexcited gas must only be able to absorb certain photons in the entire spectrum. It could only absorb some of them, okay? It couldn't absorb all of them. Now, this also supports Planck's hypothesis that matter is quantized. So remember quantized, ladies and gentlemen, what that means? It means that matter contains its energy in discrete bundles, like little discrete packets. And energy from matter can only be released in discrete packets. So when we're talking energy, ladies and gentlemen, we could, if we really wanted to, go and calculate the energy of the photons that would be found at each of these points. Okay? So Bohr modified his experiments slightly because that's what you do in science. You don't just run one trial and call it good. You play around with it, right? You test out different theories. You find different angles in order to study your hypothesis. So he modified his experiment and he took a glowing or excited gas. Now these would be the ones we'd play with in class for our lab. So, and he would energize these gas with heat or electricity. We use electricity to get the gas particles going in class. I'm so bummed we can't play with these. It's so much fun. Okay, one of my actually it's one up there. If I had to pick a favorite lab to do, this is up there in that list. Okay, so I really am bummed. And I'm working from home, as you guys know. I can't even go to school and set this up and film it, which is really disappointing. Anyway, so you would take this gas, heat it up with a bunch of electricity, and then you would shine the light through a prism or a grating. And the grating that we would use in class are a device called a spectrometer. And so you would then see the bands of light that have been emitted from this gas. So, ladies and gentlemen, this is called a bright line, or a bright line spectrum, or a line emission spectrum. Now, he concluded that an excited gas must only be able to emit certain photons, just as that cooled gas can only absorb certain photons, which also supports that quantized, like Planck's idea of quantum mechanics and energy being quantized and matter being quantized. So this evidence helped Bohr come up with his explanation for the atomic model. So when you look and compare your absorption spectra and your emission spectra, you can see they line up beautifully. Okay, so we'll look at this. So this is the hydrogen emission spectrum. And I'm fairly certain we have hydrogen at school, so we'd be able to see this emission spectrum at school. And with this emission spectrum, you can see, well, it lines up perfectly with the absorption spectrum. Okay, so if an element can absorb certain photons, well, it seems logical that the photons that it's able to absorb are the same wavelengths or energy levels that it's going to be able to emit. And that's what we see here. So if hydrogen can absorb this wavelength of purple when it is cold, when it is excited, then it can emit this. Neat, eh? Okay. Now, every single atom, ladies and gentlemen, has its own unique spectra. This is aluminum. Okay. So every element has its own unique atomic spectra. And if aluminum was heated up to the point it was a gas, this is what its spectra would look like. So same idea. And then if we jump back, though, and compare it to hydrogen, it is distinctly different. Now, what's really, really cool about this spectra is because every single atom has its own emission and absorption spectra. Astrologists are astronomists. Not astrologists, because it's Monday. Astronomists. People who study the stars, not the people who pseudoscience make up fortunes based on when you were born. That's silly. People who study the stars, astronomers. That's the term we're looking for. It's Monday. Really, it's Wednesday, but it's still Monday's fault. You guys miss me, really. So for what they do is they can take and analyze the spectra of stars, planets, or stars or nebulas, what have you, any gas in space, and analyze its spectra and figure out what they're made of. That's how we know our sun is primarily hydrogen and helium, because we've analyzed the spectra of it, and which is awesome. So because we can't just saunter up to our sun, grab a sample, and analyze it for what it's made of. We can't do that. But by understanding the spectra, we know what the stars and planets, or stars and nebula, are made of. Isn't that awesome? I think it's awesome. All right. So, ladies and gentlemen, let's also think, if we're going to be analyzing spectra, where would we want our telescope? On Earth or orbiting the Earth, such as the Hubble telescope? Orbiting the Earth. Why? Because the atmosphere would be interfering with those wavelengths. It would be absorbing and reflecting and refracting and bouncing them all over the place. So, therefore, you have to go into space to analyze these things properly. So, enter Hubble telescope. All right. So, ladies and gentlemen, Bohr came up with an idea to explain how an atom can be absorbing or releasing these quantized amount of photons, these quantized photons. So, his explanation is that within the atom, there are certain allowed energy orbits or energy levels around the nucleus. And the electrons can move around and orbit in these energy levels without giving off energy. Now, I know it sounds weird, and it is 100% more complex than this. And I have another video on YouTube on the Google Classroom, another YouTube video that kind of goes into beyond where this all goes, and done very well. And just so you know, we're kind of just getting a bare bones introduction in with this. You can spend your entire life studying this and still never have all the answers, which is so cool about science. The more you learn, the more you realize you don't know. All right. So that meant the energy of the electron in the atom is quantized. So just as Planck hypothesized. So an electron can have this amount of energy or this amount. It can have this or this. It can't have anything in between. No gradients. This energy or this energy. That's it. Okay. Now, for the electron to occupy any one of these particular energy levels, it must possess the exact amount of energy allowed to be there. It can't be found in between orbits. So if you are in an area that says, oh, 4 electron volts, you must have 4 electron volts of energy. Now, when an atom is going to absorb a photon, it's going to gain energy, okay? And that electron can go up an energy level. Now, it has to absorb the exact amount of energy to go to that exact energy level, okay? And it can't absorb half of it. It can't absorb part of it. So that is where these spectra come in. So here, these spectra are representative of the not that one, that's the bright line spectrum. These spectra here are evidence of absorbing energy and an electron moving up to a certain energy level as it absorbed that photon. So, cool, hey? Yeah, it's cool. Now, if an atom is going to emit or release a photon, the electron will move down to a lower energy. And it absolutely has to release an exact amount of energy to go back down to that energy level. So if it's emitting a photon, that's the bright line. And to determine the amount of energy that is released by a particular electron, you can look at the wavelength of the beam of light in its spectra. I really like emission and absorption spectra, in case you haven't noticed. Okay. So, ladies and gentlemen, beautiful diagrams here. Okay. So, ladies and gentlemen, what we've got is, here is our equation. The energy is the Planck's constant times speed of light times the wavelength of the light. So let's assume this wavelength, or the amount of energy that's in this light, is the exact wavelength, or the exact amount of energy that is necessary to take the electron that is here in this little red energy level. It can then bump that electron up to the next energy level. This is what we see in the absorption or dark line spectrum. Okay? So, ladies and gentlemen, what we have here, this energy level at the bottom is called the ground state. And that has a low energy state. So you guys remember from chem, and when you guys are talking about the energy state of electrons and how electrons like to be in the lowest possible energy, and how the valence electrons, when they're not in a complete octet, they are unstable. So they want to tend to fling off electrons to become stable, to have that complete octet in the outer layer. That, like lithium, for example, any of those alkali metals, they're just going to be pitching their lone electron around left, right, front, and center. They don't want it. It's too high energy. Same idea here. This is the ground state of the electrons. Electrons like to be low energy. So they're not going to stay like this for ages. This would be your bright line spectra. Okay. So when you're going to heat up a gas, you are going to cause it to absorb some energy. That will excite the electrons. Well, the electrons, they don't want to be excited. They want to pitch off any extra energy. They want to be in that ground state. Lower energy is more stable. So therefore, this electron is here. Well, it doesn't want to be there. It wants to go back to ground state. So in order to go back to ground state, to jump down there, it has to release a photon. It's going to release a photon with the energy that is the exact amount of energy for it to go from here to here. So if it takes 2 electron volts to go from here to here, it will release a photon which has 2 electron volts of energy. And then it will be content back to ground state. Cool, eh? Yeah. So this guy here is what you would see with a photon absorbed. And this guy here would be your photon emitted. Cool, eh? Yeah. All right. So, ladies and gentlemen, how this is represented is in energy level diagrams. Now, energy level diagrams are a really nice, simple way to demonstrate this. And it's really cool. So how an energy level diagram works is it shows essentially where the electrons are allowed to be, what energies these electrons are allowed to have. So along the y-axis, you're showing the different energy levels, and they are not equally spaced out. They're unevenly spaced. Technically speaking, there isn't any x-axis here because moving side to side to side doesn't mean anything on an energy level diagram. It just looks pretty, and physicists tend to like graphs, so they like x-axes and y-axes, so they gave it an x-axis because it looks pretty. Okay, so this is the energy level 1, energy level 2, energy level 3, energy level infinite. Now notice these energies are negative. Now, I know it seems kind of confusing, but it's essentially the energy that is needed to leave the electron. The Khan Academy video that I have shared in Google Classroom with you guys, along with this video, does an excellent job of explaining where these negatives come from. And so when I'm done explaining this bit, I want you guys to go watch that video because they do a way better job of explaining it than I could with the technology I've got. All right. So, ladies and gentlemen, ground state here is negative 13.6 electron volts. That's where the electrons really like hanging out. Okay. This ground state here is the level closest essentially to your nucleus. Okay. And this is where electrons are going to occupy this when they're unexcited. Now, if you give enough energy to an electron, it's going to leave. It's going to leave that electron. It's going to ionize. Okay, so remember, think back to chemistry. So remember what ionizing is? To become an ion. So in this case, it would become a positively charged ion. That electron would leave. Okay? So remember how hydrogen atoms love to pitch out their only electron and become H+, so just a lone proton, which then goes to form your hydronium. Anyway, that's chem. I like hydronium ions too. They're fun. Okay, so ladies and gentlemen, back to this here. Now, these particular values in your diagram are going to vary from element to element. Why does that make sense? What empirical evidence do we have of that? The spectra. The spectra vary from element to element, and you can calculate what these energies are based off of the spectra. The spectra are different, the energy levels are different. Isn't that awesome? Okay, so ladies and gentlemen, the calculations that we're going to be using for, Bohr spelled wrong. And then I go and spell it wrong again. Aren't you glad I don't teach you English? I am glad I don't teach anyone English either. There we go. So they're based off of the laws of conservation of energy. So recall that our change in energy is equal to the energy final minus the energy initial of any particular scenario. And remembering, ladies and gentlemen, that our delta E is equal to the energy of that photon and which also is equal to hc over lambda, or h times the frequency. Okay, so that is going to be your strategy that you're going to use when you're going to be approaching these questions. Okay, law of conservation of energy and these equations here. So that is your strategy, ladies and gentlemen. Ladies and gentlemen, also vital, if delta E is negative, that means the energy is being released, and therefore you're going to have a photon emitted. Try not to write on my face here. There we go. If delta E is positive, it means energy is going to be absorbed, and therefore a photon is going to be absorbed. Okay, so ladies and gentlemen, for those of you who've done Chem 30, you guys remember calorimetry, and when you have a delta H that is negative, it means the reaction's exothermic, and a delta H that's positive, it means you have an endothermic reaction. You could think of it as the same principle about your signs here. In this case, it's negative because the photon is emitted. Energy, the laws of conservation of energy are still valid because the energy isn't destroyed. It's just lost to that atom. It's being released from the atom. And these signs are from the perspective of the atom. So if delta E is positive, that atom has more energy than it did initially. Whereas if delta E is negative, that atom has less energy than it has initially, and the energy is just zipped off in the form of a photon. Neat, eh? Okay. So, ladies and gentlemen, I hope you guys are starting to get an inkling for those of you who are going to go on to take Chem and Physics in university, that the lines between Chem and Physics really start to blur in this area. They absolutely do. Okay, to the point they're actually completely indistinguishable from each other. So what I want you to do, ladies and gentlemen, I want you guys to pause the video here. I want you to go onto Google Classroom, and I want you guys to watch the Khan Academy video. What do I title it? I have to jump over to my other computer to check the title here. It is called Atomic Energy Levels, Quantum Physics. I want you to go watch that Khan Academy video. It does an excellent job of explaining why these values are negative, and has got some really good visuals on how all this stuff is explained. So pause the video, go watch that, and then come back. We're back! Okay, I'm assuming at this point you've already paused the video and watched that other video, Atomic Energy Levels from Khan Academy. All right. So, ladies and gentlemen, practice problems. Oh, yeah. So, ladies and gentlemen, we have a particular energy level diagram. These are lettered A, B, C, and D for the purposes of the question. And here are the varying energy levels. Okay. So, let's scroll down to have a look at question number 1. Determine the energy of a photon absorbed or released as an electron makes a transition from D to B. Okay, well, an electron is here, and then it is going to make an appearance here. Well, let's think about this. We have gone from a higher energy state to a lower energy state. Okay? Anytime you have to do any calculations, we're going to be using our law of conservation of energy. All right, so delta E, the change in energy, is equal to the energy of that photon. Okay, because that photon, whether it's absorbed or released, is going to be the energy changing. Okay, well, delta E, we're starting at energy D, and we're finishing at energy B. So it's energy final minus initial, so that means we're going to be energy B minus energy at D. Okay, we've been given energy levels. So at D, our energy is -2 electron volts, and at B, it's -10 electron volts. So we're going to put in our numbers. So our delta E is equal to, so B minus D, and B is our -10 electron volts, and we're going to subtract that from our -2 electron volts, which is going to give us a delta E value, ladies and gentlemen, of -8 electron volts. Okay, now sig digs, as always, I want 2 sig digs because all of these, the lowest number of sig digs is 2. So my change in energy, or the energy of the photon, is 8.0 electron volts. Now, why did I drop the negative here, ladies and gentlemen? The electron itself does not actually have negative energy. Remembering from the video that I just asked you to watch that these negative values are indicative of the amount of energy needed to leave the electron to get up to 0 and ionize. Okay, so to go from here to here, what has happened? What does that negative tell us? What does it tell us? Come on, you guys can do it. Released. Ladies and gentlemen, it means that that photon was released. So to go from here to here, what has happened is we have had a photon of 8 electron volts taken off. Sounds good? There's 2 ways that you can also get this value. If it goes down in energy level, it will have to release a photon. If it's going to go up in energy level, it's going to have to absorb a photon. Sounds good? All right. So we're going to jump on to question number 2. All right. Determine the number of photons of a different wavelength that could possibly be produced due to an electron at level C moving to the ground state. Okay, we're going to go and back up to our diagram here. Now, from the video that you watched, I'm assuming you've watched. If you haven't watched it, pause this and go watch it. I'm going to switch colors here. I'm going to do blue for question 2. So we're at C. I'm going to go to ground. So as you've observed in the video that I told you to watch, there's different combinations and different ways that an electron can move down from here. Well, it could go from here to here. Well, that, ladies and gentlemen, is one possible wavelength. It could go from there to there. Okay, that's another possibility. So that's 1, 2. Or it could go from here. Once it's here, if it's going to get to ground, it's going to have to go here. So that means if it goes from here to here, it'll release one wavelength. If it goes from here to here, it'll release another. So it's going to release 3 possible wavelengths as it's going to go to ground state. Cool? Cool. All right. So, and if you still haven't watched the video, go watch the video. It's a good one. Okay. So 3 wavelengths. And see diagram above for the work. Excellent. So, question 3. Oh, come on, computer. There you go. All right. Determine the wavelength of a photon required to ionize an electron that was initially at ground state. Is the photon absorbed or released? Well, all right. Ladies and gentlemen, let us go and have a look-see at our diagram. We want to ionize an electron here. Okay. Am I reading the right question? Yeah, no, I'm not reading the right question. There we go. I'm on the wrong page. Sorry, guys. Okay. All right. So, ladies and gentlemen, what we've got is we need to go and look at our diagram again. Sorry, it threw me off when I was looking at the wrong spot. Okay. I'm going to switch my color to green because I can. So we're at the ground state initially. Okay. That means we are down here at negative 14 electron volts. Now, if we're going to be ionizing this electron, it's going to have to go all the way up to 0 to ionize so that electron can take off. Okay. So then, ladies and gentlemen, once we can use this to calculate, or delta E, to calculate the energy of the photon. Once we have the energy of the photon, ladies and gentlemen, we can use our E equals hc over lambda to get our wavelength. Okay, so that's going to be our strategy here. All right. No, scroll down. There we go. Okay. So, ladies and gentlemen, what we've got is we need to find that energy necessary to ionize this. So delta E is equal to our energy final minus energy initial. Energy initial was at our ground state. So our change in energy here, energy final, 0 electron volts. Okay, so that's ionization. And then minus our energy initial, which is ground state, so which is negative 14 electron volts. So ladies and gentlemen, our energy level is going to be equal to positive 14 electron volts. Our value is positive, so that means photon going to be absorbed. As well, ladies and gentlemen, we also can tell that it's going to be absorbed because we are moving to a higher energy level. Okay, so we now have our delta E of 14 electron volts. So my next step, ladies and gentlemen, is the energy of the photon is going to be 14 electron volts. And I'm trying to find the wavelength. So I'm going to rearrange this equation to isolate for lambda. So those guys are going to swap places. So lambda H is equal to hc over the energy. And I'm going to go to my lovely data sheet to get the value for Planck's constant. Ladies and gentlemen, pick the electron volt value for Planck's constant. So my H value for Planck's constant is 4.14 times 10 to the negative 15 electron volt seconds multiplied by 3 times 10 to the power of 8 meters per second. That, off your data sheet, speed of light. We divide this by our 14 electron volts. Plonk that into your calculator, and with sig digs and rounding and units, we have 8.9 times 10 to the power of negative 8 meters. Ladies and gentlemen, I could also challenge you guys to go and figure out where on the spectrum it is. Sounds good? Cool. Try that just for fun, because you can. Why not? Okay, ladies and gentlemen, we have question 4 here. All right. Ladies and gentlemen, an electron at ground state, keyword, is in the atoms is struck by a passing electron having an energy of 9 electron volts. The atom's electron absorbs as much of the energy as possible. Determine the kinetic energy of the passing electron after it collides with the electron in the atom. Okay, this is a tough one. For the diagram above, I'm going to use pink. I haven't used pink yet. So I'm going to scoot back up to our diagram. Now, 9 electron volts is the kinetic energy that this particle had. So all of the initial electrons, the electrons within the atom, were at ground state. This electron is going to be hit with an electron containing 9 electron volts. It can absorb anywhere from 9 or less, and it's going to absorb as much of it as it can. Now, this is where the tricky part of this question comes in, ladies and gentlemen, is that these electrons are only capable of absorbing energy within these pieces. They can only exist at their given energy levels. They can't go anywhere in between. So this electron could go from here to here, or it could go from here to here. Well, we had 9 electron volts in the passing electron that collided with this guy. It's going to absorb as much as possible. The most it could absorb would be 7. Because it could absorb 9 or less. Because if it was to absorb 9, it'd be up in here, and that's not possible. It can't exist there. So that means, ladies and gentlemen, 7 electron volts is the electron volts that this electron absorbed. Okay, so let's go back down to our question here. We've got, once again, ladies and gentlemen, delta E. Have to do our math, can't just talk about it. All right, is equal to the energy that is final minus energy initial. Don't need to put that in there. There we go. Okay. Oh, by the way, this is your principle number 5 on the back of your data booklet. There we go. Okay. Now, ladies and gentlemen, remember how our energy absorbed is going to be only 7 electron volts, okay? So, our EK initial of that initial photon is going to equal our kinetic energy that of our kinetic energy final, okay, plus the energy absorbed. Okay. All right. So, ladies and gentlemen, let's do this guy first. The change in energy, E final minus D initial. So this will be the energy of the delta E, change in energy. So we've got energy level, where it can go to, which is C. Oh, goodness. There we go. Minus energy level at A. Recalling, we got 7, that's as high as it could go. Okay. Minus our negative 14 because it was initially at ground. So that means it absorbed 7 electron volts of energy. So that we've already talked about and got that number logically. This is just the equation to show it. Okay. So we know that we've absorbed 7 electron volts of energy from this remaining, or from this electron. Well, remember, ladies and gentlemen, that our kinetic energy final is going to be equal to our kinetic energy of the electron initial. And once we rearrange the equation, we're going to minus it from the energy that has been absorbed, okay, which is our 7 electron volts. So, ladies and gentlemen, we are going to take the 9 electron volts, which is the initial energy of that passing electron, and then the electron in the atom absorbs 7. So therefore, the kinetic energy of that passing electron is 2 electron volts. Now, sig digs is your 2.0 electron volts. All right. Sounds good, ladies and gentlemen? All right. All right. We're back. Technical difficulties solved, ladies and gentlemen. So let's look at question 5. So a photon with a wavelength is released from an atom that returns to an unexcited state. So this bit here tells us a whole bunch, ladies and gentlemen. Released, that tells us that our change in energy is going to be a negative value. Keep in mind, that's important. And it's going to return to an unexcited state. That means it was excited, and then it's going to release a photon and go back to the ground state. So it's going to go to the ground state. If the ground state has an energy level of negative 9.92 electron volts, that means this is going to be our energy final, ladies and gentlemen. What was the initial energy level occupied by the electron? So the first thing we need to do is we need to figure out, well, how much energy does this photon have? The energy that the photon has is the amount of energy that is going to be lost by that electron. So let's find our, whoops, I forgot to write my E. There we go. We're back. Delta E is equal to the energy of the photon. So the change of energy in the atom is equal to the energy in the photon, which is our hc divided by lambda. We have lambda, so that's good. So the change in energy that is going to be experienced by the atom is going to equal the energy of the photon. Planck's constant, ladies and gentlemen, for electron volts, okay, because this is an electron volts. Where'd it go? Okay, this guy's an electron volts, so keep it in electron volts. Make your life simple. Okay, so 4.14 times 10 to the power of negative 15 is your Planck's constant in electron volts. C is 3 times 10 to the power of 8 both from your data sheet. Lambda, we have been given that. And the change in energy with that electron is going to be 7.30588 electron volts. There is something that you need to do here now. What is it? You need to make this number negative. Why? Released. The photon is released. That means the energy is going to be lost in connection with that atom. So I'm going to make this green so it stands out. Negative. Okay, you need to make this guy negative here. Okay, due to that released statement. Okay, that's the key. All right. So, ladies and gentlemen, well, remember that the change in energy is going in and out of an electron in an atom is going to equal its final energy state minus its initial energy state. Well, we are trying to calculate where it was initially. Where was it sitting prior to this photon being released? So we're going to rearrange this equation. Once you're done rearranging, you are going to have our equation looking like this. Our initial energy is going to equal our final energy minus the change. Okay. So our final energy, ladies and gentlemen, is this guy. That is where we ended up in the ground state after releasing that photon. So negative 9.92 electron volts minus our negative, don't forget this guy's negative, and use all values in your calculator, negative 7.305 ... And once you plonk that into your lovely calculator, you're going to wind up with negative 2.614117 ... electron volts. Sig digs, rounding, all that good stuff. There are 3 sig digs up here, so I want 3 sig digs here, so 2.61 electron volts. Oh yeah. So, ladies and gentlemen, let's think for a minute about a couple of things we can look at with our answer to see, does this number make sense, and why does it make sense? So first of all, let's pretend that you forget to turn this number negative. This number here. If you forget to make this negative, how could your answer here indicate to you that you made a mistake? If you forget to make this number negative, you are going to wind up with something like, I think it's negative 17. I did this earlier. I think it's negative 17. Yeah, negative 17. You wind up with negative 17 negative 17 electron volts. We're just testing gravity. It's still working, according to my calculator. So negative 17 electron volts. Why does that number not make sense? Well, it's a number more negative than the ground. And you can't have any energy lower than the ground. So it'd be a really unexcited atom. It'd have be sucked into the nucleus at that point. So that's not a possible number for this scenario. Now, so that's another way that you can indicate a possible mistake. Let's say for some reason you wound up with a positive answer. Why would that be a problem? Because the energy levels are negative. And they are negative because it's a representation of how much energy is needed to leave the atom. So if you have a positive number, you've done something wrong somewhere, because a positive number would be more energy than was necessary to leave the atom. And there's no positive numbered energy levels. Okay, so a couple things to keep in mind as you're doing your calculations, ladies and gentlemen. And now, practice problems. I've got some here for you guys. And then we've got a few more down here for you guys to take a crack at. All right, ladies and gentlemen, I hope you guys have a good rest of your day. No fires, injuries, or explosions. And now I need to get this turned off. There we go. See you guys later.